I'm from the Florida Institute of Technology. We're here presenting our project that we completed with our senior design team, R3mora, the Resin 3 printed mission-oriented research assistant. The goal of our project was to develop a small diver-deployable ROV. We were inspired by ROV systems such as the Blue ROV2 and the Deep Tracker underwater controller. The Blue ROV2 is a great off-the-shelf commercial recreational ROV that can be used for a wide range of scenarios, but it's not very much designed to work with the diver. We wanted to build a vehicle that was small, compact, and would work in conjunction with the diver. Okay. Rather than being separate and having to be controlled completely from the top side. We wanted to utilize 3D printing for our manufacturing process so we could create a very customizable, low-cost ROV. We wanted to build a working prototype that we'd be able to take into the marine environment and test. And we wanted to explore the feasibility of this concept via our prototype.
So as Parker said, we wanted to use 3D printing to create our vehicle, and the 3D printing process we chose is stereolithography, which uses a 3D printed resin cured by UV light. So the picture on the left is the printer we used. It's the Anycubic Photon Mono X, and in our previous research last year at the Oceans Conference, we published a paper on the material properties of this resin. And so we created little compression testing samples. We used an ASTM standard to compression test those samples. And then from there, we took those material properties, we applied it to finite element analysis through CAD software. And we took a little small enclosure and compression tested it in that picture you see on the right. That is a pressure tank. So we imploded that sample and it went kaboom. And from that we found that our material properties from finite element analysis matched our crush depth within 5%. So our goal in this project was to apply that research for our vehicle. So this is the R3mora. Not sure if you can see it, or you can hold it up. But it is a tethered vehicle that attaches to the back of a scuba diver's tank. So the scuba diver who has attached to them will hop in the water, remove the vehicle, and they're able to explore places that they wouldn't have otherwise been able to explore. So imagine you're a recreational diver, you're not cave dive certified, but now you can go out and peek into those caves and get some cool footage. So that opens the possibility of exploring shipwrecks too, if you're not certified to go into those. And this vehicle also applies more towards to additional divers like military divers and tech divers who need a scout almost to go ahead of them.
So based on those missions that we wanted to accomplish, we came up with a set of design requirements. Our main design requirement was to have 6-degree freedom rollbox so the vehicle would be able to navigate those very tight spaces like shipwrecks and caves. We wanted it to be rated for, in this initial prototype, for the recreational diver, which limits out to about 130 feet, but still give them the ability to go down a little bit deeper if needed. We wanted it to be a fairly quick ROV, so that way when the diver is working on a limited air supply, say a normal dive lasts about 45 minutes, the diver would be able to maximize the distance that they can cover. We wanted to have a camera mount inside of the vehicle, so that way we could stream video back to the diver or back to the topside station to get that valuable data about the scenario that they're going into. And we wanted ports for expansion, so we'd be able to add additional sensor packages or figure out different camera systems or things that people would want to expand onto the vehicle. So for the vehicle design, we ended up using 2 different pressure chambers. One holds the electronics in the front of the vehicle, and the second chamber holds the battery and additional motor connections. Our motor setup is a traditional vector thrust with the 4 motors on the front and the back and 2 altitude thrusters. This setup works well with some off-the-shelf open source software that made for easy controllability. We then used Blue Trail Engineering cobalt connectors because they're easily able to be switched on and off at the surface and allowed us to take the vehicle apart. We included line guards along the side for diver safety. When you're diving underwater, you may have additional lines from your surface marker buoy or your downline that you're following. We wanted to make sure that the vehicle would not get caught up and be an endangerment for the divers. Modularity was a big consideration for our vehicle. We wanted it to be completely be able to be taken apart, parts replaced, parts swapped out. So the pressure chambers have a rail system on the side that uses a standard bolting pattern, and then we can add or subtract different modules for your scuba tank mount, different motors, GoPro mounts, whatever you need to assemble the vehicle together. The pressure chamber design is fairly neat. Since we have the ability to 3D print these pressure chambers, we could add penetrations along the sidewall. So these penetration holes right here would be very costly to add under a traditional manufacturing method like 5-axis CNC. But with the 3D printing, we're able to do this for very low cost and get the benefits of the better cable management. With the penetrators along the side right here, we're able to run the wires directly into the enclosures and not have to run additional cable management around the vehicle, further reducing the overall size. The pressure chambers also have the rails around the outside, and once we had our geometry, we were able to use the technique from our past published paper to find the safe working depth of the vehicle. For the vehicle that we have currently, we estimate the safe working depth to be about 50 meters. However, since it is 3D printed, if you needed a deeper depth or a different set of requirements, you could change that internal geometry, add ribbing or other thicknesses to the individual sidewalls to go deeper to wherever the mission requires.
So the picture on the right is from our slicer software that we use to print the vehicle chambers. And on the left, you can see we tried to play around in the beginning with the supports involved in printing these pieces, but we found that it was best just to print on the build plate directly and have no angled parts that required supports. And then for the penetration holes, we did mess around with those supports internally, but we chose to just ignore the supports, and at the end we post-processed the holes to make sure they're the correct diameter before moving on. So this is a diagram of the electronics involved. Many of you who are familiar with the Blue Robotics architecture might recognize some of these names, but we have two different chambers. One is the battery chamber, that's the larger chamber used to power the vehicle, and then the second is the electronics chamber. So what you see on a blue ROV2 is about a 10-inch chamber that contains all those electronics, but these components are squeezed into about a 5-inch chamber, and we're able to do this because our motor controllers are integrated into our thrusters. But you'll see that we do have the Pixhawk flight controller and Raspberry Pi and the FXTI for tether communication. So this is what it looks like on the inside of that smaller chamber. We have 3D printed mounts used to compact everything and make it smaller to fit inside those chambers. And on the right, you see a picture of what our control software looks like. This is called Q Ground Control, and it is also a Blue Robotics standard control software that is used to control the vehicle. So how does this vehicle interact with the diver? The vehicle sits on a scuba tank mount, which hugs the scuba tank with those yellow hose clamps that you see. And you might ask and say, well, some scuba divers might have a different type of BC, which is their backpack pretty much while they're scuba diving. So how do you account for that? Well, the piece in the green versus the piece in the blue are two separate pieces, so you can kind of rearrange based on your scuba diver configuration for more personalization. And the actual vehicle itself has a rail system that it sits on, so it slides into that mount, and from there it is connected to two pieces. So one is the scuba retractor, which holds upward force on the vehicle so it does not fall out when you're swimming around in the water. And then the second is the pin, which is keyed, so the scuba diver is able to remove that pin or insert it back in, and then they don't have to worry about the vehicle falling out when they're above the water.
So once we had the design of the ROV done and our prototype made, we got to do what, in our group's opinion, was the most fun part, going out into the ocean and actually diving our vehicle. So our first deployment was off of the coast of St. Pete during our school's marine fields projects trip. We were able to put it onto the diver's back, get some extra buoyancy on it to make it all neutrally buoyant. We took it down, practiced removing it from the diver's back, We also drove it from a topside case and simulated what it would be like if the diver had that underwater controller that we're hoping to develop. And we got to see how responsive the ROV was, how it was to swim with the diver. I was actually the diver in this photo, and we were very surprised and happy to know that the ROV made very little difference to the diver. Once underwater and everything was neutrally buoyant, it was quite comfortable to dive with and very unobtrusive. Our next deployment was in a pool where we were able to better demonstrate the process for removing the R3mora from the diver's back. So here's Susie removing the vehicle. She took out the pin. Once the pin is removed, the vehicle is able to be slid off of the scuba tank mount. You can see the two-part mount on her backside. With the vehicle in front of her, she is able to remove that retractor that is helping hold it onto that mount. You put the retractor onto your BCD so you don't lose the pin, so you don't lose the clip. With the clip undone, the vehicle is now able to be deployed. When the underwater controller is next developed, this would be the point where the diver would pull out their controller and then deploy it for their mission. Our last deployment was at Blue Heron Bridge. This is a great shore diving site in South Florida. We were able to deploy it onto a small little shipwreck in about 25 feet of water. Here we were able to fly the ROV around and get some pictures of it and in its operating environment one of the operating environments that we had identified.
So the whole cost estimate of the ROV, if you were to buy everything off of the shelf, no overhead or anything like that, is about $3 grand. And Parker mentioned an underwater controller. So for our future research, we would like to create some type of handheld device that the scuba diver can use seamlessly with the ROV. And it would ideally it looks like something that you see in the top right, but that's not waterproof, so there would be a lot of design involved with integration and waterproofing. And then the tether reel that is connected to the ROV, we've seen in the past that people have just wrapped it around their wrist or something, and as a diver, that is unsafe. So we would like to see some type of tether reel system for the diver to hold on to. And the dynamics of the vehicle, as you saw in the pictures, we just zip tied foam on there for now, but we would like to create a custom buoyancy fairing that is calculated to work with this vehicle. And something unique about integrating with scuba divers is that everyone has their personal preferences. So we would like to create the ability for the diver to separate the two halves of the vehicle. And to do this, we would use a wet mateable connector that replaces all of these topside connections through the sidewall. So the diver can just pull it apart and attach each piece of the vehicle to a different part of themselves, like their thigh or to their chest.
So overall, we were able to create our working prototype of the R3mora. We were able to dive it underwater and examine some of the different ways that it affects the diver. We also demonstrated that utilizing the low-cost MSLA 3D printed pressure enclosures, we could make a very customized low-cost ROV. And we also showed that a tool like this might be very valuable for recreational scuba divers, professional scuba divers, and the dive professionals of the world. Thank you all for attending our talk. We have our vehicle up here for after the presentation if anyone wants to come see it. Thank you.
Thank you guys. I want to congratulate you guys for the wonderful presentation that you have done, and
Thank you.
we are very proud of two young scientists like you. You guys did this very good job. Congratulations. So guys, do you guys have any question about this interesting talk? Yeah, can you yell from there?
Yeah, so two questions. One, what was the print time on your 3D printing? And the second was, did you ever test pushing it kind of past that safety factor, obviously in a safe way, but pushing it past that safety factor to see where you have failure?
So the first part of that question, our two different chambers had different print times because the print times for SLA is just based on the height of what you're printing. So that first big chamber was about 36 hours to print, and then the second smaller one was about 20 hours to print.
The bigger one and then our smaller one. For going past the depth rating, this vehicle itself has not been past that depth rating that we calculated. However, in our previous paper, we made small form factors of these pressure enclosures with the penetrations along the sidewall and that unique geometry, and we were able to estimate the crush depth within about 5%. So we're fairly confident in our estimations, but since it is 3D printed, there is always a little bit of variability in the part, so it may be able to go a little bit farther, or it might be a little bit less, but that's why we add that 3x safety factor on top of it to make sure that the diver would not experience a failure, especially when it's on their back, so close in proximity to them.
We have time for one more question.
I saw how you unattached it once you get to your second one. Is there a need and can it be reattached or returned?
Yes.
Successful?
So to reattach it, that gear retractor that gets clipped off of the diver's BCD gets reclipped back onto the vehicle, and that provides a positive force to feed it back up into that mount. Our current version of the mount did not have an area quite wide enough to help guide the vehicle in. But if you made that guide area larger, the retractor would have enough force to almost pull the vehicle back onto your back with little effort. But since you always dive in a pair, when we dove it, Susie actually helped me guide it back onto my back when I was struggling a little bit the first time that we used it. But definitely the idea is to have it come back onto the diver's back, so that way when they get back to the boat, the system is fully back to the diver and it's not needing surface support to pull it back on.
Okay, thank you very much. It's a very interesting talk.